In this video, we'll be learning about potential energy, one of the two main types of energy we learn about in physics. Potential energy is a stored up energy due to an object's location relative to its surroundings. There are two types of potential energy that we'll deal with in this chapter. Those two types are gravitational potential energy and elastic potential energy. We'll learn more about each of these two types in the next few slides, starting with gravitational potential energy. Gravitational potential energy is stored energy that's associated with an object's position relative to a reference point. The reference point is something that you will often have to define for yourself. Typically, it's not given to you. We'll choose a reference point, which is also sometimes called a reference level, at a point that is convenient, that makes the problem easier. Often our reference point or our reference level is the ground, or the lowest position the object can reach. The equation for gravitational potential energy depends on the mass of an object, the gravitational acceleration on Earth, or on whatever planet you're on, times the height of that object above the reference level. You'll notice that this equation includes the gravitational force in it, because the gravitational force is mass times gravity, mass times gravitational acceleration. As with all other types of energy, this is a scalar, which means you don't plug any negative numbers into the equation, with the exception of one thing sometimes. The one thing that can be negative when you plug it into this equation is h. H is negative if the position of your object is below the reference level. Otherwise, mass is always positive, and g is always positive in this equation. So that you know, your textbook uses the equation PE equals mgy. But this equation that I've written here is the more commonly accepted version. So let's look at a problem that uses this equation. In this problem, number 24 in your textbook, a 350 Newton child is in a swing that's attached to ropes, and these ropes are 1.75 meters long. We're going to look at how much gravitational potential energy this child has at three different positions: when the ropes are horizontal, when the ropes are at an angle, and when the ropes are vertical. I'll start by drawing a picture so that I can label on my picture where my reference level will be. So there's my child on the swing. This is when the ropes are vertical. Here's when the ropes are horizontal. And we'll switch to a different color for part B, when the ropes make an angle of 30 degrees. So I have three positions here. This first one is A, this second one is B, and this third one is C. I know that the length of this rope is 1.75 meters. That doesn't change. But I have no idea how high this child is from the ground. Therefore, the most convenient point for my reference level is the lowest point in the swing. That's where the child is at point C, and the ropes are vertical. In A, my ropes are horizontal, and I want to know how much gravitational potential energy does this child have. You'll notice that I'm told that this child is 350 newtons. Because that's measured in newtons, that can't possibly be mass. Instead, that's the child's weight. And for this problem, weight is equal to gravitational force. Well, we know gravitational force equals mg. It's an equation that we are given. So, as I'm calculating the gravitational potential energy of this child in part A, instead of putting in numbers for m and g individually, I will just plug in 350 newtons for those two letters, mg. Then I have to plug in a height. Well, this child in swing position A is 1.75 meters above the reference level. You can see that because 1.75 meters is the distance from here to the reference level. It's the length of the swing, and that's how high off the ground that kid is. So 1.75 meters is what I will plug in here. When I multiply 350 and 1.75, I get 612.5 joules. That's the amount of gravitational potential energy this child has at this point. Part B is where the ropes make a 30-degree angle with the vertical, as shown in black here. For part B, I will still have 350 as m times g. But I will have a different height. To figure out that height, I'm going to draw a different triangle here. There's my 30-degree mark, and there's the swing in the vertical and in the horizontal position. I'm not going to worry about drawing the rest of the swing, just the ropes. I know that this entire distance is 1.75 meters, and I know that this entire distance is 1.75 meters. The thing I'm looking to find is this distance right here. That's how high it is off the reference level, which is located down there. To find that distance, this small distance in green, I'm first going to find this distance here using trig, and then I'll have 1.75 minus this distance in blue equals the distance in green. To find this distance in blue, I would use the cosine function. The cosine of 30 degrees is adjacent over hypotenuse. So it's this blue leg divided by the hypotenuse, or 1.75 meters. And that gives me a blue leg of 1.516 meters. 1.75 minus 1.516 gives me the height. So my height is 0.234 meters. When I multiply 0.234 times 350, I get a potential energy of 82.06 joules. So that's my answer to part B. In part C, our swing is located at the reference level. Remember, we said the reference level is a position where the potential energy is equal to 0. Because the height is 0, you are no distance above the reference level. So in C, the potential energy of this child is 0. We'll use and calculate the potential energy in many more problems to come, but we're going to move on to the other type of energy now, and that's elastic potential energy. Elastic potential energy is potential energy or stored energy caused by deformation. We will often deal with this type of potential energy as we're talking about springs and stretched or compressed springs. But other objects can have elastic potential energy. For example, when a tennis ball hits the ground, it squishes a little bit. That ends up being some elastic potential energy, which then gets converted into kinetic energy as it bounces back up. For the purposes of this class, we will only calculate elastic potential energy as it deals with springs. To be able to understand about this type of potential energy, we first need to understand some things about springs. The first thing we're going to learn about springs is something called the spring force. This is the force that a spring exerts on an object that's attached to a spring. To calculate the spring force, we use something called Hooke's law, named after a famous physicist named, I believe it's Robert Hooke. He discovered that the spring force, or Fs, is equal to negative kx. K in this equation is something called a spring constant. I'll talk more about this spring constant in a moment. X in this equation is the distance that the spring is from its natural resting position. So, for example, if this is a spring that has nothing lying on top of it, and this is the same spring that has a box on top of it, X would be the difference in length of these two, or X would be this distance here. X, as we know, it's a distance, it's in meters. All forces are measured in newtons. So what's the unit of the spring constant? If you answered newtons per meter, you are correct. It tells us how stiff or how loose the spring is. A spring that's difficult to stretch or difficult to compress, we call that a stiff spring that has a very high spring constant. Whereas a spring that is very easy to stretch, easy to compress, that has a low spring constant. Spring constants can range anywhere from 1 or 2 newtons per meter to thousands or hundreds of thousands newtons per meter. In general, the spring constant must always be a positive number. One other important thing you'll notice about this equation is the negative sign. That tells us that the spring force always acts in the opposite direction of the displacement of the spring. So this object displaced the spring downward. As a result, the spring force pushes upward on the object. Now that you know a little bit about spring force, let's look at the equation for elastic potential energy. As I mentioned, we only calculate elastic potential energy for springs. It can be different for different objects. We'll call it U sub s, and the s indicates that we're talking about a spring. The equation is 1/2 kx squared. K is the same thing, the spring constant, but x in this equation is the displacement from equilibrium. So if we were to have an object hung from a spring, and it naturally hangs there, and then we were to stretch that object so that the spring is nice and stretched out, x in this energy equation would be the difference between this level and that level. So this right here would be x. It's a little bit different of an x than what you see in Hooke's law. Let's look at a few problems that deal with these two equations. This first problem talks about the spring inside of a stapler. We're given the spring constant, and we're told what its relaxed length is. And we want to know how much elastic potential energy is stored in the spring when its length is 0.15 meters. Again, the equation for elastic potential energy of springs is 1/2 kx squared. So 1/2 times 51 newtons per meter. To find x, we need to find the difference in these two lengths. 0.15 minus 0.115. That gives us a length of 0.035 meters. And of course, don't forget to square that x. Once I plug that all into my calculator, I end up with a potential energy of 0.0312 joules. A very small amount of elastic potential energy. In this next problem, we're looking at an object being hung vertically on a certain spring. We're first going to look at what the spring constant is, and then we're going to estimate how much that spring would stretch if a different block was hung on it. For starters, I'm going to draw a diagram or a picture of what's happening here. There's my object being hung on a spring, and it tells me that the spring stretches 2.76 centimeters. Well, if I draw a free body diagram for that object, gravity would be pulling it down, and because that spring stretches, the displacement was downward, so the spring force must be upward. Remember that negative sign in Hooke's law. This object is just chilling there. It's at equilibrium. So the net force acting on this mass is equal to 0. Well, the net force is spring force minus gravitational force equals 0. So that means the magnitude of the spring force must be equal to the magnitude of the gravitational force. Now remember, when we don't have vector symbols on force equations, we don't plug in negative numbers. That means that when I plug in the equation for Fs, I leave off the negative sign. No negatives are allowed when we only have magnitudes. So Kx equals mg. That means that K, the spring constant, is equal to mg divided by x. The mass of this object is 2.5 kilograms. G is 9.8 meters per second squared. X is given to us as 2.76 centimeters. Now, of course, we must convert that number so that we have 0.0276 meters. When you plug that all in to your calculator, you find that we have a very large K. 887.68 newtons per meter. While that's a large number, that is still a very reasonable spring constant. Part B wants to know how far the spring will stretch if a different block is hung on it. Take a moment now to try this problem on your own and see how you do. Okay, let's go through part B. It's still true that the net force acting on the object is equal to 0 because it's at equilibrium. So that means that the spring force is still equal to the force of gravity. Kx is still equal to mg. But this time we're going to solve for x. X is mg divided by k. This time my mass is 1.25. So 1.25 times 9.8 divided by that value for k that we found tells us that this spring has been stretched 0.0138 meters, which is equal to 1.38 centimeters. I can tell this is a reasonable number because it's a smaller number than when we had the larger mass on it. When we had the larger mass, it stretched a total of 2.76 centimeters. This time it stretches half of that, 1.38 centimeters. Again, we will work more with these equations in future problems, but hopefully this serves as a good introduction to these types of energy so that you will understand them and be able to use them in the future.